Okay, good afternoon then, everybody. I hope you can hear me. My name is Mark Richmond. I'm the product manager for our CW fiber lasers at SPI Lasers, and it's good to have you with us for this afternoon when I'm going to be talking about how having a variable beam quality means that we're able to increase the manufacturing flexibility and productivity of our lasers. So let's just start with a quick overview of what we want to see for the for our session. Get the next slide to come up. So I'm going to just run through a very quick introduction to SPI lasers and the cube fiber lasers, which are the ones that we are using for our variMODE product, and then come on and talk initially about why we want to have a variable beam quality laser. And the answer is because of the effect that beam quality has on laser cutting. And I'll then talk a little bit about what this feature is and how it operates. And then we'll look at some results in terms of cutting and piercing and welding that we've done using the variMODE feature on the lasers. And finally, I'll talk a little bit forward-looking on where we might be going with this type of technology and what exciting new things that it might bring as well. And finally, we'll just summarize all that and see where we've been during our time together this afternoon. So hopefully it's going to be an interesting time. There's quite a lot to get in, so I'm going to talk quite quickly, but I believe if you've got some questions, you can add them in through the webinar questions forum. So just a very quick excuse me, look over the company that we're talking about here. So we're with SPI Lasers. They're a UK company. Now focusing totally on fiber laser manufacturing and innovations for fiber lasers, but we've been around as a fiber laser company. Well, we've been dealing with fiber lasers since the early 2000s, but there's a history going back much further than that. SPI Lasers itself was founded in 1999, but there's an industrial laser background within the company now that goes back to the 1980s, so you're looking at different types of industrial lasers. But as we're going through, we're always introducing new products, and the ones that we're talking about now are within our Red Power Cube and Prism range, and those were started around about 2016. What are we involved with? We like to think that it's more than just the laser source. We want to try and get a complete understanding of the business that we're involved with, not just from the side of producing and manufacturing lasers, but also how the lasers are used. And so we do a lot of work in-house ourselves, looking at application development and looking at complete solutions for our customers, using the experience that we've built up over many years in terms of what the laser can do, how it can be best be used, what are the features that will best make that laser appropriate for a particular type of application. Today, we're going to be focusing on the CW side of the business. There's also another large part of SPI's business which looks at pulse lasers, mainly for marking and engraving. But here we're going to be looking at the CW side of the business, particularly where we're focusing there on cutting, welding, additive manufacturing, and some micro machining. And the Cube product range, which was introduced in 2017, has got a number of parts to it. We've got water-cooled lasers from 300 watts up to 2 kilowatts in a 19-inch rack format. And then air-cooled lasers in a similar format from 100 to 500 watts. But when we go to a floor standing cabinet, we can take the power levels from 3 kilowatts up to 10 kilowatts in our current product range. And just as a starting point for what we're looking at today, we have always made those lasers with a number of different fiber diameters, and the different fiber diameters have a slightly different beam profile coming out of them inherently, and also a different beam parameter product, which I'll just mention later on. So we've already had lasers with a fixed beam parameter product, but one that could be selected from the range that was available as options at the time the laser was purchased. So some of the advantages that differentiate our laser maybe from other ones. When we look at the higher power lasers, then we have an inbuilt pierce detection feature inside the laser. Pierce detection, when you're cutting, allows a real increase in productivity, something like 10 to 15% against a system with no pierce detection. We have built back reflection protection as standard into the beam delivery fibers that we use with our lasers. We call these P/Q. They're a QBH compatible mechanical fit, but with extra features to give this enhanced back reflection protection. Inside the lasers, we also have pulse generators, so we're able to do pulse shaping and high-speed modulation, which allows a lot of fine machining and also gives great control over welding applications. And as I mentioned, we have got a range of mode profiles or beam profiles from the delivery fibers, so that there is already a choice, a fixed choice, let's say, to optimize the process performance. And what we're looking at now is an option for real-time selection of the beam profile. And finally, on the high power lasers, we also have a low power mode, which sounds a bit strange, but when you've got a 6 kilowatt laser, you might want to cut something out and then mark it just with a part identification. At the high power, you normally can't control the laser low enough to allow that marking, and so we have a special feature that allows it to run stably in a very low power mode, and that it also is a feature which is found to be quite useful. So a number of features and differences about some of the SPI lasers. Why do we want to use the laser for cutting? Well, first of all, the laser has a number of advantages when used in cutting, and most of these are now well known, and the lasers are fairly ubiquitous in laser cutting applications. But they allow great flexibility to address a range of materials and thicknesses of those materials, so that the laser is becoming very well used. If we try to look at what sort of range of lasers materials we could use, then this graph is just trying to show how thick you could cut different materials with different thicknesses, different powers of laser. And as you can see on some of them, particularly the red mild steel bars, there's a bit of shading, particularly when you get to the higher powers at the top end. And really that's a point which we're going to come to more and more through this discussion today, is that you know, what is a good cut, and what is the limit to your cutting capability depends a little bit on how you define the edge quality that's acceptable for your process. And that's where the grayed out or the shaded part of these graphs is important. It shows you the limits that you might say, well, I can cut through at that thickness, but it's not a very good cut. If I slow down a bit or go to a slightly thinner material, I can make the cut quite nicely. And we're going to be looking at how we can improve that cut quality as we go through today. But fiber lasers in particular, coming into the into cutting, they give us, compared to other types of lasers, really high efficiency. If you think about a neodymium YAG laser, that would be about 3%. You may get up to 10% with a CO2 laser in terms of efficiency, but a fiber laser is easily at 30%. We've got now a large range of powers. As we looked at, we can go up to 10 kilowatts and higher now, but yet there's still lasers down at 100 watts. Fiber optic beam delivery is very good for integration. It's flexible and it's easy. And obviously with a fiber laser, it's kind of inherent in that the beam starts off in a fiber. You might as well keep it in a fiber all the way through to the workpiece. And we can get some very good beam qualities. We saw earlier that it's possible to get single mode lasers at the diffraction limited performance. And now those lasers are up into the kilowatt regime. But yet they're still quite small compared to some of the older types of lasers. The fiber lasers have a much smaller footprint and fit much more easily onto shop floor environments. And the operational costs are low for a fiber laser. There's no gases being used up, no flash lamps to replace. And these days the capital costs are dropping as well. So that there's a very good business model for using a fiber laser in very many applications. But in terms of laser cutting, the perceived wisdom was that CO2 lasers would be the laser of choice. They've been used for many decades for high power metal cutting, although recently fiber lasers have been encroaching on their market, and it's about a 50-50 split between CO2 lasers and fiber lasers, probably just slightly in the fiber lasers. More of those are going out on new cutting systems. But fiber lasers give a cutting speed advantage over CO2 for thin materials, but were not considered to give a very good edge quality in the thicker material. And just as an aside, we just talk about what we mean by edge quality. Generally, we're characterizing this by a measure of the surface roughness. And the surface roughness is measured using a device shown in the bottom left there, a small probe that you can move over the surface of the material, and it's measuring the peaks and troughs as shown in the little diagram on the right. And you sample various positions at the various lengths and work out a value for the surface roughness, which is usually given in micron. So we did some work looking at different thicknesses of material and trying to cut them in the best way with various beam qualities, various beam parameter products of the laser. So the beam parameter product for a laser beam is given as the product of the diameter of the beam at its waist and the far field divergence, and that's something that's called the beam quality. The BPP by convention uses the radius of the beam and the half angle far field divergence, and because it's the multiplication of a diameter of a distance in millimeters and the divergence in milliradians, then the units are millimeters milliradian. And so as you go to a beam with a worse beam quality, the number gets bigger, and as you go to a beam with a better beam quality, the number gets smaller. So a diffraction limited beam for a fiber laser would have a beam quality, a BPP of about 0.35, something like that. So these beams that we're looking at here, if you look at the numbers on the table, there are a large number of times diffraction limited beams, but they're typical for beams coming out of 100 micron delivery fiber. And so looking at the results, you can see that at 10 millimeter thickness, the BPP has little effect on the edge quality. and then you might think to start to see some effects at the 15 millimeters. By the time you get to 20 millimeters, you can see that visually that cutting with a 5.8 BPP gives you much smoother finish than the 3.2 BPP, and that's borne out in the measured roughness values, which you can see on the right hand side there, where the roughness is down by a factor of 5 when you increase the BPP. So this is the key kind of result that we want to start with as we think about variMODE is that, yes, as you increase the BPP, you can get a much better edge quality when cutting thick section mild steel in particular. And actually it works in converse for thin materials. You can actually cut slightly faster when you've got a lower BPP. But this effect is really, as we've looked at in our results, very much linked to the actual BPP. So that even when we keep a constant spot size on the workpiece, we still see these results. As the BPP increases, the edge quality gets better. So it's not just to do with the spot size on the workpiece, it's certainly the effect of the divergence coming into this as well. And if we look at those values and sort of plot them on a graph here, we can see there's a sort of a step change in the roughness, around about 4.5 millimeter milliradian, and maybe there's a slight ongoing improvement in the roughness as you take the beam quality up above that. But what this would indicate is that by having a simple high BPP, low BPP change, we can access the improved edge quality for thick materials and yet still have the ability to cut thin materials with the performance you get from a low BPP laser. So we want to introduce now variMODE as a feature of the laser that will allow it to take advantage of these two different processing regimes. And just by way of a bit of background, there's quite a lot of patent technology out there about different cutting with different beam profiles. Two areas that have been looked at are shown here. One is where you use different laser modules with a beam combiner to combine them into different areas of a delivery fiber, into the ring or into the core or into a cladding ring, or alternatively you use some other method or mechanism for steering the beam across the end of a fiber with different delivery regions, and those produce a change in the spot size that's coming out of the fiber, and also a change in the beam profile, but on the end of the fiber itself. But variMODE, we're introducing a novel approach to changing the beam quality of the fiber lasers, in that all the energy for the variMODE laser remains in the fiber core, and none of it goes into a cladding ring, and therefore we have no need for special profile delivery fibers. The standard sorts of delivery fibers work very well, or are all that are needed for variMODE. We've shown variMODE can work across the whole of the current power range of our lasers, up to 10 kilowatts, but that it has capability to go even higher than that as needed. And the other thing about it is that the main difference between the variMODE is that we've been looking at changing the beam quality, but we do that through changing the spatial profile distribution within the fiber core, and so we have more energy moving out to the edges of the beam. If we look at this, which is the sort of change in beam profile that we're looking at for variMODE. We're moving from a cone-shaped beam on the left-hand side, and then we can switch that in a short time, here less than 40 milliseconds, to more of an annular beam with steeper sides to it. So that's where the energy has been pushed out to the edges of the profile. And this switching can be done through the control of the laser, but we find that the cone-shaped beam with a low beam parameter product is optimized for fast cutting of thin metal sheets, and particularly for those with highly reflective materials like aluminium, copper and brass. But it's also very good for high quality piercing in thick sheets, and we'll look at those things later on. And similarly, for the high beam parameter product mode, that's very good for the good edge quality on thick sheets, and it cuts through very well. So kind of before variMODE, you had to make a compromise. If you had a range of fiber options available to you, you could choose a low beam quality, low beam parameter product number if most of your work was for cutting thin sheets, but then you'd struggle when you wanted to cut thick material. Or the other one is, you might have chosen something for optimized for cutting the thick sheets, but then when you came to cut the thin materials, you'd find that the productivity was down because you weren't cutting as fast. So this is where having a variable sheet, variable beam parameter product really helps you, is that you're able to optimize for both processes and you haven't got to make the compromise. So you might think, what's going on through the cutting, which is allowing this change in the processing. So it's inside the laser itself that we make the difference to the beam and have the mechanisms which are changing the output beam through the delivery fiber. But keeping all the energy within the core means that divergence changes on the output of the fiber. And that's what this graphic is trying to show. Here we've got our low BPP value, which is something like 3.3 millimeters milliradians, and the beam forms a narrow beam through the cutting head, and then we get this cone-shaped output in the focal plane. But if we change to the higher BPP value, then we get a larger beam through the cutting head, there's a bigger cone angle coming down to the focus spot, but the actual focus spot's diameter is roughly the same, but with more of the energy pushed to the edge of the beam. And the top level of BPP we've set at around 5.5 millimeter milliradians, and that allows it to match the acceptance angle of most standard cutting heads, which is around 0.13 Na. So that 0.13 Na is the total energy of the beam. Usually when we're calculating the BPP, we use a measurement which encloses 86% of the energy. So there's just a little bit of an allowance that has to be made on top of the calculated angle from the BPP to encompass the whole beam, and that's the number that needs to fit through the cutting head, as kind of shown in this simple graphic here. Let's have a look at some of the results. So first of all, we looked at cutting the thick steel with our high BPP value. And usually when you're trying to cut thick steel, if you try to cut out fine features, such as this little strut here at 2.5 millimeters wide, then it's very difficult because you tend to get heat build up from one side to the other, that leads to a lot of melting once you've got such a thin piece of material. But actually, we're finding that with the high BPP, you can get a lower level of heat input into the material, and these fine features can be cut out. And if we just think about cutting thick materials, this is the comparison we wanted to make between the low BPP, where if we tried to cut it at a reasonable power level and a reasonable speed, you can see that the surface here is not very smooth. If you look at the top of the cut, there's a lot of what we call nail file, that sort of fine grooving going on, and then there's a number of gouges out of the material, leading to an uneven surface deeper down in the material. That's because of some of the ignition of the oxygen that's used for cutting through the material. So thick steel cutting with a low BPP isn't really very acceptable, but if we can change that BPP with variMODE to a high value, you can see now that we've got a very smooth finish. There's a shorter length of that nail file, and it's much less pronounced. The effect is that you get a very good surface finish using this very standard grade of mild steel. You don't have to use anything special, no laser grade steels are needed, but it's easy to cut and get a good surface finish with a reasonably wide process window as well, because that's the other thing, is the robustness of the cut. How insensitive is it to variations in the material surface finish, bulk quality of the material, and any movements with the cutting system. And the high BPP here gives us a very robust solution. On the other hand, as we said, we might want to use the cone profile with a low BPP, and we might want to look at cutting some thinner materials. And here at these power levels, the difference between thin and thick is sort of 10 millimeters or something. So when we talk about thin, we're not talking about foils, we're talking about materials in a few millimeter thickness range. So the cone mode not only gives us a faster cut, the better edge quality, but it also allows us to get less dross on the material. And there were some results just to highlight that. So here at 3 kilowatts, we could cut 2 millimeter stainless steel with a similar edge quality, but about 45% faster when we use the cone mode compared to the other mode. And at 4 millimeter stainless steel, we were cutting about 25% faster. So you might look at these cutting speeds if you're very familiar and say, well, maybe I could cut a little bit faster with that power and that thickness of stainless steel. So again, the results we're putting up here aren't necessarily the fastest ones, but they're what we call our production speeds. They're ones which have a reasonable process window and allow a fast setup time. So they're kind of the speeds that would be sensible to use in a job shop type application. If we move to slightly higher powers, and here we're looking at what we can do with a 6 kilowatt laser, we can see that we have cut the 2 millimeter stainless steel significantly faster. But again, it's a significant improvement if you can use the cone-shaped profile with the low BPP value. And on a reflective material like brass, we were able to cut again at sort of 25% faster. And just on the next slide, we're going to watch that in action as we cut some shapes out of brass with these two lasers. So we're sort of looking at a side-by-side comparison of the two conditions. So the top one is showing what we've called the low BP, the low beam quality, which is the higher BPP mode, and the bottom one has got the cone shape profile, so it's cutting faster at 7.5 meters a minute. So overall here, although the cutting speed, linear cutting speed, is 25% faster between the 7.5 and the 6 meters a minute, the productivity, if you like, is about 12% increase between the 47 seconds and the 42 seconds. And that's because of the real world conditions that we're using there, like the jump speeds are the same. There's the time for piercing, there's the time for the acceleration and deceleration of the stages, etc. But, you know, even so, it's a good 12% increase in productivity. I think most of us would be quite happy with a 12% increase in productivity. We could probably work for an hour less each day if we could be 12% more productive. So there's certainly some advantages in doing that. And then the other part of the story about variMODE is the piercing. And just going to start off looking at piercing in some mild steel. But, you know, as we know, when we're cutting, say, a large sheet out with many parts, many nested parts, that there can be many pierces needed, which have to be done before each start of each cutting part. Sometimes we can do those pierces on scrap metal, and it doesn't matter what the pierce is like, we just need to get through the metal. But oftentimes we have to do a pierce inside a good part, and we don't want to have a lot of spatter coming out onto the material. So what we're going to look at here in this little video is get rid of that pointer. Video to run. Excuse me, I'm just going to get rid of my pointer so I can get the video to run. Lovely pointer when it works, but it doesn't help in running the video. Okay, so this is 20mm mild steel. We're cutting through with our cone shape with a low BPP value. We're pulse piercing here. If you can hear the sound, we're pulsing about 30 Hertz. This gives a very reliable pierce, and we had about a very, very low number of failures in the piercing with that regime. Although the pierce was about 10 seconds, you saw the pierce on for about dwelling for about 15 seconds, just because there's no pierce detect on this setup, and we needed to be sure that we cleared through the piercing. So with that cone shape profile, with the low BPP value, we're able to pierce through very quickly, very reliably, and can give a very neat profile of the cut. You can see there's that, although there's some sparks, there's very little spatter is produced around the pierce. And if we look at those in a little bit more detail, you can see in the picture on the left that those sort of pierces taking place in about 10 seconds give us a very small top hole and a very neat exit hole from the pierce. When we tried to pierce the same material and tried to get a good low spatter hole with the high beam quality with our annular beam, we found a much more deformed hole with much more spatter around it. and at 6 kilowatts we could do that in 18 seconds, but it took us about 30 seconds when we did it at the 3 kilowatts that we were using for the fine piercing that we did. So we find that with piercing, having a low BPP value allows us to pierce much more neatly and in a much faster time than we can do with just the high BPP mode, which is very slow and gives a lot of spatter. And this really then summarizes what's the advantage of a variMODE laser in cutting applications, particularly even if you're only limited and want to cut thick materials, is that you have the ability to do very neat, fast pierces before you quickly switch to the high BPP value and do your cutting at a good speed and get a very smooth edge quality out of it. And that's the main message on cutting, is the advantage of variMODE. But there's more to it than that. It also has some effect on welding, and we just have not investigated this quite as fully at this stage, but looking at some initial results with a 6 kilowatt laser, again looking at here in mild steel. We did some simple bead on plate welds at this case about 5 meters a minute, and you can see that the two different beam profiles give us very different weld geometries, in that the cone shape gives us a narrower weld which is fully penetrating, but at the same speed the other weld, the other profile, the annular one, gives us a much broader weld and not so deep, so that without having to change anything in the focus position at all here, or the optics, we're able to give us one type of weld which may be better to give us greater tolerance against a fit up in a butt weld, and the other one may give us a deeper penetration which may be better for some overlap welding type applications. So it tends to show us that variMODE laser allows us to be very versatile in our applications. So let's just have a look at what it brings us overall. First of all, it's no good having a very good quality feature if there's no way to control it. So fortunately with cube lasers we have a very good control system which is called FiberView, and we've been able to integrate variMODE into the FiberView interface. We can control it either through the built-in pulse shapes of FiberView, or through a digital input onto the machine control interface. And the good thing about the machine control interface on FiberView and the cube lasers is that it's configurable. So there's 7 inputs and 7 outputs, but about 30 functions that can be chosen to fit onto those hardware pins, and that allows different configurations of the lasers for it to be controlled to match up to whatever is the choice of the system integrator. So tight integration of the control of variMODE into the laser. And just in summary then, we've got beam profiles which we can tailor for the application, thin, thick materials, both for welding and cutting, and not forgetting the advantages for piercing. When we look at thin materials, we're able to give ourselves a very fast process speed and still maintain a good cut quality. At the high thick materials, particularly mild steel, the emphasis is on good cut quality and maintaining a reasonable cutting speed. The difference with variMODE is that it's all in fiber core technology. We don't need special delivery fibers, and the setup is all done with inside the laser itself. And because we've got this difference in beam divergence coming out. If we're in a defocus range, we can change the spot size without having to use a focus head if we want to. So there's some applications we've looked at where we can vary the spot size by defocusing a fixed amount and keeping that fixture. The spot size will change if we change the profile. One of the advantages we looked at, or one of the differences we looked at for the variMODE is it's all in the fiber core, and the whole of the power of the laser is available in that fiber core for any of the profiles that we use. If we think back to one of the earlier slides when I was talking about other IP that's out there, if you put the difference of the modules spliced onto the core and the cladding of a fiber, then the power that you get depends on the ratio of those modes, those modules into the different positions on the fiber. But that's not a limitation for variMODE. All the power is available for all the profiles. Because this is done inside the laser, you don't need any extra optical components. There are steering beams or anything like that, which could increase the complexity of your system and the risk of damage through optical contamination. We've got better flexibility for our systems. If we don't have to think about building a system just for cutting thick material or just for cutting thin materials, we can build one system, and by varying the laser, can use it across a wider range of applications. And as we've said, we've got a simple user interface for good control and integration of variMODE. So I think what variMODE so far is bringing us is the message is you don't have to compromise in the choice of your fiber laser if you did have a choice. If you'd chosen a high BPP laser to cut thick materials with good edge quality, then the price of that would have been that you'd have reduced speeds for cutting thin materials. And on the other hand, if you'd chosen a low BPP laser to give you fast cutting of thin materials, you'd have found that trying to cut thick materials would have given you poor edge qualities. So the advantage of having variMODE is that there's no compromise is needed, and you can have the best laser output for both cases. So in England, we say that means you can have your cake and eat it. You get both things together. But we don't want to stop just there with variMODE. We think there's more things that could be coming with it. And so we've been looking at the next generation, which we're calling variMODE Pro, and that's kind of waiting in the wings. So as I talk a little bit about that, which is quite exciting, but I need to just have a bit of physics, hopefully not too much, to try and highlight where this is such a radical new technology. So generally, when we talk about single mode beams, we think of a Gaussian profile, and that might be the little picture on the bottom left there. In free space, that profile is called a TM00 beam, but within a fiber, the mode would be LP01. But you can also have single high order modes propagating in a fiber, and those have numbers like LPX1, and as the X varies, you get more lobes on the building up on the profiles, which are shown in the right hand side. And as you increase the number X, the M squared for that mode increases. So although they're starting to look like rings, they're still single order modes. They're just not a mixture of modes. But so normally we'd think of a flat top beam is a mixture of a large number of modes. But these ones, although they've got an odd shape, that we're not usually used to. They are single high order modes. And the difference is, so if I have produced a ring beam by feeding the power of, say, a fiber laser into the cladding of one of these core and cladding fibers, I actually am producing a mixture of modes. And although if I image the end plane of the fiber, I'll see a ring, as the beam propagates away from the fiber, that beam would tend to fill in the middle and start to look like a sort of Gaussian beam, maybe a bit spiky, but just as shown at the right-hand side of the bottom there. But the difference is with these modes is that even though you propagate away from the focus, you still maintain that ring structure, or sorry, that lobe structure on the system. If I try to go here, I should be able to get there. So what these are showing is some experimental results, and it's taken from a beam profile, which has taken slices of the profile at a number of places through the focus, and it's trying to show that as you go from one side to the other, that ring structure with the number of 6 lobes maintains constant throughout the focal position of the laser. So that this means that you'll be able to process out of focus, but still have the ring structure. And that is something which none of the existing systems can do. That even if they produce a ring at the end of the fiber, by the time you're out of focus, and remember, for a lot of focusing, cutting applications, you're cutting out of focus with the focus either inside or above, usually above the workpiece. And so where the beam interacts with the workpiece isn't a ring. In this case, wherever you look at, it would be a ring on the center of the workpiece, and therefore you get all the advantages of that distribution of energy to give you a smooth profile. And we've just done some very quick results looking at some welding, actually. Bead on plate again. We've just kept a constant power density on the workpiece, and changed this beam quality from a single mode up to a beam parameter product of about 2.3. This is coming out of a smaller diameter fiber than we were looking at for the previous variMODE work, which was 100 micron. This is smaller than that. But we've just been able to show that by keeping the power density constant, we can change the width of the profile of this bead by a factor of 2.6 times here. And so these are just some preliminary results that we've taken, but the penetration is maintained because we've kept the same power density on the surface. And the difference between that and normally what you do, which is defocus, is that because we've managed to keep the same power density on the surface, the penetration hasn't varied as much as it would normally do. So this is interesting new work that's going on, and as I say, it's still in very early stages, so we're not saying too much about it at this stage, but it's just to say that with variMODE technology, we're very much looking at starting from a point which is already bringing advantages into the customers, but we've got more areas that need exploring, and enhancements will be coming along in next generations. So just to tie it all up a bit, I want to just summarize some of the advantages about fiber lasers, and particularly about variMODE. So fiber lasers, we said, many advantages for laser cutting processing, but it's been difficult to find single laser that's good for all types of laser processing to do with a cutting. And so SPI Lasers has introduced variMODE on its cube fiber lasers, and that allows the user to change the beam quality of their laser in real time to select the best beam parameter product and the best profile for the individual processes. And that's available across the whole range of high power lasers. And although this is already bringing good results, there's further advantages planned and in the wings for it. So when we talk about variMODE, what we mean is we're talking about an all-in fiber core technology that allows us to use a standard delivery fiber. It means that we can use all the power of the laser that's been purchased in any of the modes. We don't need to predetermine the maximum power in each mode. We're changing the energy distribution and not the power density. So when we're working in the focus, we've got the same, roughly the same spot size, whichever beam parameter product we're using, but we've changed the energy distribution from the cone shape to more of an annular shape. And we can do the switching in real time, so that if you have been doing a pierce and then a cut, you can come down and pierce, and then in the time it would take you to move the head to the cut height, you can have switched to the other beam profile. So there's really a very flexible approach to beam parameter variations for fiber laser cutting and welding applications. So thank you for your time. That's basically the summary and the main part of the talk. I've got a bit of time left, and I see there's some questions have come in, so we'll try and have a quick look. If you give me a couple of seconds, I'll just look through the questions that I've got and then see which ones we can answer just now. But if there's any I haven't got time to answer just now, we will pick up on all the questions that have been sent in and try and answer them at a later date. And if you want any more information or you want to contact us, then just go to the SPI Lasers website, and we can you find a way of contacting us there. Okay, so there's a few questions here. I'll just try and quickly run down some of them. So just quickly, one person's asked, does polarization play a role in cutting and piercing? And there are some thoughts that polarization effects do come into play, but that isn't part of the effect of variMODE. And in fact, all the lasers that we've been talking about this afternoon are unpolarized lasers. So there's a random polarization between the S and the P planes. And we've been asked what's the difference between laser piercing and drilling. Effectively, a pierce is a drill, drilling a hole in the first instance through the material. The reason we talk about it as piercing is it's done for this particular application of just starting off a cut. And if you were trepanning, then it would be very similar. You'd pierce through a trepan's hole. So you could move the beam in a small circular shape and call it a trepan's hole. But the thing about piercing is it's generally focused onto the materials at a thickness that you want to do some cutting afterwards and not use the hole in its own right. I mentioned pierce detection during the talk, and someone's asked a question about what does pierce detection do? Does it stop when the laser has drilled through the material. And yeah, that's effectively it. The pierce detection that we have built into our cube lasers allows the laser to know when the hole has pierced through the material. And although the laser itself doesn't automatically stop, what it does is it gives a signal to the on that machine control interface I talked about, which allows the system integrator to have full control, that he can then stop the laser pulse if he wants to, or he might want to keep the laser turned on but then just start the cutting phase. It just tells him when to start moving the head to start cutting. So pierce detect basically tells you that you have gone all the way through the material. So we've been asked that we looked at materials thicker than 20 millimeters, and most of the work with the power levels and the lasers that we've got have been looked at using 20 millimeter as the top. We have done some work, a little bit of work at 25 millimeter mild steel, and we get very similar results. The piercing and the cutting improvements are both there for these types of material, but we haven't done a lot of work, and so I wasn't presenting those results this afternoon. But yes, so we have got that capability to go to thicker materials. And I'm not sure that I made it clear, but yeah, variMODE is available now on these cube lasers. So it's not something in the form of the high BPP and low BPP value. That is something which is an option, but is an option that's available on all the cube lasers from 3 kilowatts and above at this stage. So if you're interested, we'd be very happy to talk with you more about that. We've had some questions about how repeatable is the BPP value, and actually we set a specification on a plus or minus 0.3 millimeter milliradians. That's the repeatability from unit to unit, but also within the product lifetime. So we've had obviously done long tests on operating the variMODE on and off from high and low very many times for millions and millions of operations, and we still find that the BPP values remain within that plus or minus 0.3 millimeter milliradians. Yeah, and someone's asked, is it stable also with movement? And yes, within with the movement. So we have obviously like all fibers as a minimum bend radius. If you maintain the movement within the specified bend radius of the fiber, then the mode profiles actually are very, very stable. There's no problem from that point of view. Okay, that looks like a selection of the questions, and most of them have been answered. We will pick up on the ones that we haven't been able to answer fully at this time. But I think as we're coming to the end of our time, I'll leave the odd last one or two, and we'll come back to those. So just as we move on, then I want to thank you for your time this afternoon to join with SBI Lasers for this webinar on the variMODE feature. If you've enjoyed it, or possibly even if you haven't, but there's another webinar coming up on 13th of November. This one is about lasers for e-mobility, covering both pulsed and CW applications, and how they can bring benefits into this growing market sector. So we'd very much like to join with you again as SBI Lasers, and talk about lasers for e-mobility applications. But just finally then, thank you for listening in at this time, and yes, goodbye, and have a good rest of the day wherever you are. Okay, thank you very much.